Welcome everybody to iEarth Digital Learning Forum. My name is Mathias Lundmark and I'm talking to you from Oslo. And today's theme is going to be flipped classroom, or omvendt klasserom på norsk. And with us today to introduce the subject is Christine Lindstrøm, who's a physics lecturer in Australia at University of Sydney. She has a Ph.D. in physics education, and she heads a research group in physics too. She's got lots of experience with flipping, so I'm looking forward to picking up lots of good tips. And before we get started, I'm just going to say that we'll be recording this meeting, and we're going to cut out Christine's part and put that on iEarth.no. And I'd also just like to give a heads up, in case someone has to leave, that next week we're going to have iEarth Learning Forum on digital fieldwork, so super relevant for Corona times. And I think that's all I'm going to say. So Christina, I'll just hand over to you.
Okay, thank you very much. All right, so as Matthias said, my name is Christine Lindstrøm. I live and work in Australia at the University of New South Wales, where I work in the School of Physics as a lecturer. I also co-lead a new research group called Physics Education for Evidence-Centered Teaching, or PERFECT, at UNSW. As mentioned, my background is in physics education research. I did my PhD in physics education research at the University of Sydney, finished in 2010. And after I finished my education, I moved back to my native Norway and worked there for 8 years before returning to Australia. And in Norway, I was teaching physics in science teacher education. And that's where I used flipped classroom through all of my 3 years of teaching physics. And so I'm going to share my experience with doing that with you guys today. But before I get started, I just thought I would show you the wonderful people that I work with now at PERFECT. And we do several different things. We have a focus on both physics education research, but also the implementation of research-based teaching methods, hence the evidence-centered teaching part of our research group. So if you want to check out what we do, then please go to perfect.physics.unsw.edu.au. But to the topic of today, flipped classroom. So I worked in science teacher education at Oslo Metropolitan University from 2011 till 2018. And there I was mostly working on teaching physics to both primary and middle school teachers to be. Now, some of you might be familiar with how science teacher education in Norway works, but to those of you who are not, I just thought I'd give you a brief introduction. So the science teacher education program is 4 years, and students do the equivalent of 1 full year of science divided over 2 years. Now, science covers a whole lot of different fields, as you know: biology, physics, chemistry, science education, technology and design, and geology and meteorology, which means that physics only really comprises about 20% of the full course. Now, the way this was organized at Oslo Met was that I basically had about 7 sessions, each of almost 3 hours, to cover the entire Physics 1 course, which was quite a big one. The entire course grade was based on the exam, and the cohorts were ranged from 11 to 32 students. So relatively small student cohorts, which made it quite nice to work with because I got to know my students. I learned about flipped classroom during my PhD in physics educational research. And so the reason why I approached my teaching this way was because I'd already been convinced of the reasons why you would want to use flipped classroom instead of the traditional teaching methods. Now, the focus on my talk today is not on the arguments for why flipped classroom is good. So I'm not going to spend any time on the literature. Instead, I want to spend a bit more time on showing you how I actually implemented different aspects of a flipped classroom design in my particular course in teaching physics. So the underlying teaching philosophy when it comes to flipped classroom is that instead of focusing on content that needs to be covered by a lecturer, we change how we think about what happens in a course to instead focus on a set of very clear learning goals that we help students achieve. It may not be obvious how that actually changes the teaching at all. And so I'm going to show lots of different ways in which the teaching changes when you have such a philosophy. But in essence, the main change is from what the teacher is doing in terms of delivering content to what's happening with the students. So the students are in focus, not the lecturer. So in terms of a simple overview of the course structure, flipped classroom basically means that students get their initial exposure to the material at home before they come to class, such that we free up the time in class to work with the material. And so that structure essentially enables what's called interactive engagement in class, because we're not tied up with filling class time with just covering material. So how do we know what to focus on in class? This is where a teaching method called just-in-time teaching comes in handy. So just-in-time teaching is essentially a way for students to give feedback to the lecturer before class so that that information can be used to guide what's going to happen in class. Now, once the lecturer knows what the best things to focus on in class are, then he or she can design teaching activities that will really help students engage with the material in the best way possible for learning that particular material. And so the one student active teaching method that I really want to focus on here is peer instruction, which you might have heard of before. Peer instruction doesn't just refer to any student collaboration. Peer instruction is a very specific teaching method developed by Eric Mazur at Harvard University for helping students to work with conceptual understanding of key concepts in a classroom setting. And I'll show how that works more specifically in class. So the implementation of this overall structure in my actual classes looks like this. There's activities to be done before class, then there are activities that we perform during class, and then there are activities after class. So before class, there's reading the textbook, watching some relevant videos on YouTube, doing the pre-test, also telling me what was difficult about the pre-work, and familiarizing themselves, the students, with the specific learning goals for the class. Then during class, I give some mini lectures about what the students didn't quite understand from the pre-work. I might show some demonstrations, we do some peer instruction, perhaps do some simulations in sort of as a digital or online experiment. We do some real experiments, and we do work with mini whiteboards. And then after class, students might work on some problems. They get written solutions to the problems they're working on. There are assignments, group projects, and of course, the exam at the end of the semester. I'm going to talk a bit more in detail about the most relevant aspects of this structure to a flipped classroom structure. So first, essential to a flipped classroom structure is a written set of learning goals. So as you can see here, those of you who can speak Scandinavian will be able to read some examples here. So this is a set of learning goals that are used for the topic of light. Now recall that each session was 2 hours and 45 minutes. So these are the learning goals for almost 3 hours worth of old school lecture time. And notice how they're very specific, and they're also written in such a way that they indicate something the students need to be able to do or show. So for example, draw and explain how a camera obscura works, or describe the concept of refraction, or explain and conduct calculations with the equations V is equal to F lambda and C is equal to F lambda. So it's important to not write the learning goals in terms of understand this, because it's difficult to know, like, how have you achieved a learning goal that is understanding something? Instead, if the learning goal is written in a way that you can put it directly into an exam, it makes it easier to know for the students when they have achieved the learning goal, and it's also easier for the lecturer to assess whether the students have achieved that goal. Then the students need to be exposed to the material through some materials. The textbook can be really useful. We use Complete Physics by Stephen Popple. I also gave students a set of lecture notes from the previous year, and I gave them links to a set of videos that nicely covered a certain number of learning goals. So I used a combination of these three, whatever I thought was the best way for students to achieve learning goals before coming to class. I like, in particular, Veritasium and Hewitt-Truett for physics, but in geology, there might be other websites that have really good videos. Then the students also had to do a pre-test. Now this pre-test was not particularly, difficult or comprehensive. It was merely a spot test to check that the students were actually engaging in the pre-work. So as you can see here, for each class, we had 4 actual physics questions, and students could consult all the materials they had. Students did not get marks counting towards any final mark or final grade for this. So, I didn't mind if they were consulting their books or talking to their friends, or, however they responded to these questions. But I wanted them to engage with the material. I also asked them the following 2 questions. Write 2 things you didn't understand in the pre-work, and write a wonder question for this topic, where a wonder question can be anything you wonder about that's related to the topic, but not necessarily part of the curriculum. So the point of the first of these was to essentially get the students to tell me, what is it that you need more help with, so that I could use that information to focus what we were going to do in class on what they actually needed to spend time on. The wonder questions were there so that the students were encouraged to be curious. And especially for a science teacher, it's important to be able to feel that curiosity themselves. But even for students who aren't going to be teachers, curiosity is a wonderful thing, because it enables, or forces them in this case, to try to connect the new material with what they know from before. So some experiences they've had, or maybe some knowledge they've covered in a previous course, and really try to connect new knowledge with old knowledge, which is basically how we learn. And it enabled me to get an insight into what the students were motivated to learn about so that I could frame what we were doing in class in light of student motivation. Okay, so the first year that I taught this in 2012, I didn't really give students any marks at all. Now, that resulted in a decent completion rate of the pre-work, but not quite as good as I wanted. So in 2014, which was the third time I completed this course, I gave students a little pre-work carrot. So for each of the 6 problems that they had to answer in the pre-test before each class, they could get 1 mark. So for the first 4, they got a mark if they answered correctly. And for the last 2, they simply got a mark if they had written 2 things that were difficult and if they had written a wonder question. If they achieved at least 50% of the marks from all of the pre-work, then they didn't have to do question 4 on the last assignment. So it was a pretty small incentive, but a small incentive turned out to actually have a large effect, as I'm going to show you later when I'm going to go through the results. So, lecture slides. When I prepared for class, I would make little mini lectures where I tried to explain in a slightly different way to how something had been explained in the pre-work material. What the students had told me was still difficult. For example, energy is often challenging for students, and so I decided to make a diagram like this instead of just going through bullet points describing energy or using equations. I would also use these wonder questions in different ways. So for the topic of light, 2 students actually asked where do double rainbows come from? And I thought that was a really good question. And so I was able to essentially cover almost all of the content in that class in light of where double rainbows came from. So first, I would say a little bit about how light was produced in the sun, then how the light then travels from the sun to our atmosphere, where our atmosphere is transparent to visible light. So light goes through the atmosphere down to humans, where on the way, light is refracted and reflected in water droplets in the air. And this is what actually produces the rainbow with its secondary rainbow. Then the light gets all the way down to the humans, to our eye, where it's refracted in the lens of the eye. And then we did a little experiment on lenses until eventually light is detected by rods and cones on the retina. So for the 3-hour lecture, I would give little mini lectures on each of these, because each of these 5 parts had sections that students had found difficult in the pre-work. And we did student activities as well associated with each of these 5 parts. So that really helped with the motivation for the students, because now they really saw an application of the content that covered before class and didn't necessarily see how everything hung together. Another way that I used wonder questions was to simply show a wonder question, such as this one: given that energy cannot be created or destroyed, does that mean that energy has always been in the universe? This basically just needs the confirmation. The student has understood the concept of conservation of energy correctly and thought of it in a new situation that wasn't explicitly mentioned in the pre-work. And so, yes, this was really good and just deserved a thumbs up. In other cases, student wonder questions would reveal confusion. So here's another couple of examples. I don't understand why kilowatt hours is a unit for energy, given that it's used to calculate power. And how can the unit of watt be 1 joule per second and still have the unit of kilowatt hour, which also says something about the time? So here there's total confusion, at least amongst a couple of the students. And they were not the only ones who thought that the units when we dealt with energy and electricity were challenging. And so in this case, I threw those two questions right back at the students and asked them to work in groups of 3 and decide how you would answer these student questions. And in this case, there was no doubt amongst the students that these questions were relevant because, well, they were asked by the very students in the class. All right, so I mentioned that I used a teaching method called peer instruction. I used it the first time around with flashcards. Now, it looked like this when I asked the students a multiple choice question after having given a little mini lecture. I asked them a conceptual question to check if they had understood what I was talking about. Then there were 4 alternatives, and they had to hold up their flashcards to indicate which alternative they thought was the correct one. Now, after they had shown their answers, as you can see in this case, not everybody agreed. They would talk to someone, preferably someone with a different answer than themselves. Then they would try to convince that other student that they were correct, or they might have been convinced that they were wrong and hadn't fully understood the situation, and then they would vote again. But after using these flashcards, which was a bit inconvenient, I started using Learning Catalytics, which is an online platform for letting students respond to such questions. And instead of trying to explain to you how that worked, I'm going to show you a little video of how that was implemented in class. Da setter vi I gang. Dere må gjerne logge inn på Learning Catalytics med en gang. Jeg har åpnet prøven. I teach physics to pre-service teachers, and in all my courses, I use a student-centered teaching method called peer instruction. To implement peer instruction, I use Learning Catalytics. This is a very user-friendly platform specifically developed for peer instruction. The students learn by working with conceptual questions. First, the students answer these questions individually before they discuss them with their peers. The students log on to Learning Catalytics with their mobile devices. When I deliver a question from my iPad, it appears on the students' devices. Kan jeg få de siste 2? The students are then given about 2 minutes to think about the question and answer individually. Sånn, har alle svart? Vær så god. If between 20 and 80% of the students answer correctly, I'll let them discuss their answer with a peer. Here, Learning Catalytics gives me the opportunity to pair students with different answers as far as possible. The students then discuss the question with their assigned peer for 3 to 4 minutes before they respond to the question again. Sånn, halvt minutt igjen. After this second round, I generally ask a couple of students to explain their reasoning to the whole class. Okay, som dere ser så fikk vi en ganske... My experience with using peer instruction is that the students are both active and engaged, and that their learning gain is increased. The students on the whole are better prepared for class, and they get regular experience with reasoning and arguing for their responses. By using Learning Catalytics, the discussion partner is optimized for each question because the program joins peers with different responses. Another consequence of the computer-generated pairing is a positive effect on the class environment. Og det kanskje der den analogien bryter ned. Oops. Okay, so another student active teaching method that I've used is simply using mini whiteboards. So these are little whiteboards where the students can work in groups of 2 or 3 on problem sets, preferably problem sets that are useful to visualize either with equations or with drawings. So I'm going to show you a very brief 30-second video of 2 students here working on solving a problem using an equation, and they were struggling a bit with the concept of squaring the velocity. Now, because they had written this down on the whiteboard, it was very easy for me to see what they were doing and where they had gone wrong. And so I could walk around with my colored whiteboard markers and show them. And I would like you to just focus on the girl in the middle as she is paying attention to this explanation. So there you can see how the light suddenly went on for her, and it was easy for everyone to focus on the same thing. Okay, so I've now covered how a flipped classroom course was implemented and all the different ways that student active teaching methods were involved. So for the rest of the talk now, I'm just going to cover the evaluation of this course. I'm going to include the evaluation both from 2012 and 2014, because after each year, I did improve on the course using the student feedback. And in some cases, I was surprised that there was no change in evaluation. And in other cases, it did show up in the student evaluation. So one of the questions on the student evaluation form was, how valuable were the following aspects of the physics course for your own learning? So I used 10 different aspects. It doesn't matter if you don't remember all of them. I'll be mentioning the most important ones. Now, in fall 2012, the first point to note is that of all of those different aspects of the course, none of them got an average score of less than 3.4 out of 5. So all of them had some value. But the least valuable ones were the traditional elements of the course. So the assignment, the experiments in class, solving problems, the group project, and solutions to those work problems. The best aspects of the course were all related to the flipped classroom. So we had the pre-test. There were my mini lectures based on the specific things students really needed help with. Watching YouTube videos before coming to class. Peer instruction was very popular, but to everybody's surprise, the most valuable aspect of the course was reading the textbook before coming to class. Now, as the years passed, I tried to make improvements, especially on the aspects that were, seen as the least valuable. So by 2014, basically all of them fell between 4 and 5. And at that point, I didn't really see the point in, splitting hairs and looking at the difference between them, because to me, they were all relevant parts of the course. In terms of other results, voluntary attendance in class was always high, 93 and 96% respectively, which basically meant that students turned up unless they were sick. And students were very happy with the course, and that didn't actually change through those 3 years. And one of the reasons for this was, as one student said, the course was varied and inspirational, and a non-traditional course was very much appreciated. Especially 8 years ago, this was certainly not the norm in terms of how to run a course. In terms of the amount of pre-work and course content, students thought, well, it was probably a little bit more than average, but that's how I like it. I want to stretch my students and I want them to work hard because I want them to learn a lot without being too overwhelmed. So I was happy with this. One complaint students had was that the first time that I covered the course, we had a very short amount of time, just 3 weeks, whereas we ended up with at least 5 weeks by 2014. So the students did comment on this, that more teaching over a longer period, I need some time to reflect on what I learn. And it was a shame that it was just 1 class per topic. Basically, they wanted more time to learn physics. In terms of pretest completion, this is where I told you there was no marks or no mark-based incentive the first time around for doing the pre-work. And that was visible in 2012, where only 75% was completed each week. But one student says, because there was an expectation of pre-session preparation because of the online test, and because this test contributed to defining the lecture, I felt a higher degree of mastery. So students appreciated having that input in what happened in class. After introducing the carrot, pretest completion rose to 90%. And students did indeed say that that was very motivating with the carrot. And they also felt that the fact that they had to prepare properly before each class increased the learning considerably, which is exactly the point of flipped classroom, that you get more out of class if you come prepared and then work with the material in class. And the last comment, this is a great teaching method, flipped classroom that is. You get to work on problems before class, and if you don't understand it, it's explained in class. Other results, students felt that the course helped them understand physics, not just like learn a whole bunch of facts. And they also thought that the use of varied teaching methods was a good way to learn about different teaching methods, which is very important for future teachers. And one student commented that the variation probably contributed to the feeling of time passing very quickly. When we, in addition, are left with a lot of knowledge, surely that must be a compliment. So it helped, definitely helped that we did different things through each class instead of just, 3 hours straight of lecturing would have, killed anyone really. Peer instruction was very well liked by the students. And in 2014, I included this question where students strongly agreed that regularly discussing with different peers had a positive effect on the social class environment. Students commented that I've never learned so much and it requires that we prepare for class. And I think it's been very educational to discuss with different peers and see different ways of thinking. In terms of the mini whiteboards, there were similar comments. It's easier to explain much of the physics with the help of a drawing, and when the whiteboards are big, it's also easy to share it with the rest of the class. It's nice to talk in smaller groups and be teachers for each other, which again is particularly valuable for future teachers. It was very inclusive and a great way to cooperate, and it was good that they could visualize their discussion. Plus, it's fun with whiteboards. And lastly, in terms of the different response systems I use for peer instruction, flashcards were a good way to start because they're free and user-friendly, but they're a bit clunky. I use these clickers, which I think are mostly phased out by now, but they were okay. And they had the benefit of being anonymous and with nice graphics, but they were quite expensive and a bit impractical for data storage. So I ended up with Learning Catalytics, which I was very happy with. It was user-friendly, efficient, anonymous, with nice graphics, relatively affordable, with practical data storage, really good pedagogically, and with the added bonus of improving the social environment. So, in sum, the lessons I learned from Physics 1 in developing it for Flipped Classroom was that students really valued a clear course structure, that there was a clear expectation of pre-work completion, that student feedback shaped the lecture or the content of what used to be called a lecture, there was importance of being prepared to be able to follow the sessions, and the anonymity and instant graphical feedback and partnering mechanism of learning catalytics. So the last question is, sure, it was great, they liked it, but did they really learn anything? And so here, I gave them a standard test of mechanics. So this is a diagnostic test of Newtonian mechanics that's been used all over the world. It's called the Force Concept Inventory. But only 3 out of 7 classes actually focused on mechanics. So yeah, it wasn't ideal, but at least it was a way of testing knowledge. I gave it to my students 9 months after they sat their Physics 1 exam, and I could find data from, it was given shortly after Physics 1 and 2 at the University of Oslo. Now, in short, the students performed equally well to the students at the University of Oslo, even if they'd covered less physics. And when they had covered the same amount of physics, they did better. So all in all, pre-work, student active classes, and varied teaching methods were all very well liked, and certainly a teaching method that I have continued with since I started. So thank you.